Welcome to Microlecture 53, alkene addition reactions. This one is halogenation. Okay, so we're doing the addition of X2 to alkenes. X2 can be Cl2, Br2, or I2. So we could be chlorinating, brominating, or iodinating the carbon-carbon double bond. There is a concerted curved arrow mechanism that you'll need to know. The process occurs anti across the carbon-carbon double bond, and we'll want to be able to predict the products in such a way that we can determine whether they are chiral or achiral. So first let me just show you the reaction. Br2, for example, would add across a double bond so that one bromine atom adds to one face, the other bromine to the opposite face. So that process is said to be anti. And it gives a trans product of the two bromines relative to each other. That's not the only possibility, though. The alkene can approach the bromine from the opposite face of the alkene, and we could end up with the opposite stereochemistry. Notice this is not the meso compound. There's no plane of symmetry through this molecule. So this is a 50-50 mix of enantiomers, and this is achiral. Let's do a couple of more examples, just predicting products, and then I'll show you the mechanism. So let's say that we're adding iodine across the double bond. One iodine could add on one side, the other on the other side, and we have equal likelihood of the opposite occurring as long as those two iodines are adding trans in an anti-fashion. One more, let's try this Z-alkene, and just notice that, I need to make it Z-alkene. Let's do that. There we go. So this Z-alkene is going to be chlorinated. I want to make sure that I maintain this relationship between these two groups. They're on the same face of the double bond. So that's going to dictate the stereochemistry of the product. So if this chlorine added on the wedge, then this one on the dash, and that means that there's a hydrogen atom here and a hydrogen atom here. All right, so we want to maintain that relationship. And then we also do form the enantiomer. Oh, I think my H is actually a methyl. There we go. So we've maintained the relationship between the two R groups that are on the same face of the alkene. We've formed both enantiomers. Both are possible. So let's draw out the mechanism. All right, and so if we're reacting iodine across the double bond, the alkene carbon attacks as the nucleophile. The halogen atom with its lone pairs circles back and attacks the alkene. All right, and then the other halogen atom is kicked out. So what that means is we form a three-member ring with a positive charge on the halogen, iodine in this case. All right, and so that's our first intermediate, and the iodine that was kicked out comes in for attack at the carbon that would be more partially positive, because that carbon would bear a positive charge better than the other carbon in the three-membered ring, because it has resonance with the nearby benzene ring. So this is where the attack happens, and you see that the iodine comes in and attacks the carbon and then kicks out the other iodine like a leaving group. So I want you to notice that this is very much like an SN2 reaction. Alright, so this is SN2-like, and we're going to get inversion of the stereochemistry at that site, and so that is the reason why we get anti-addition for the trans product. So this iodine stays on the dash, and the incoming iodine on the opposite face, just like it would in an SN2 reaction. And I can just draw in my missing hydrogens just for clarity. Alright, so this is one product that would form, and the enantiomer, as we predicted on the previous slide, also forms. So the intermediate, if it's chlorine in the three-membered ring, it's called a chloronium. Okay, so these are the names of the intermediates. We've got chloronium, we've got bromonium, iodinium ion, and it looks a lot like a mercurinium ion.